This is electrode potential, and this is the title topic. I'm starting with oxidation and reduction. This is my title topic. I'm starting with oxidation. What is oxidation? It is in terms of electron. It is the process it involves the loss of electron. This is our IGCSE definition. Electrode potential is the main topic. It's also called equilibria. We call it redox equilibria. The first concept we are putting is the old concept that what is oxidation. In terms of oxidation number, it involves the increase in oxidation number. Now, remember that whenever you make oxidation half equation, it is the loss of electron. And then look at the reduction. What is reduction? Reduction is the process that involves gain of electrons by a species. And in terms of oxidation number, a process that involves a decrease in oxidation number. Now look at this reduction half equation. When you make a reduction equation, you will show electron on the left hand side. Majority of this chapter follows the reduction equilibria. Okay, so we have to remember the fundamental two set of definition. Oxidation oxidation is the loss of electron, and reduction is the gain of electron. Sorry. Then I put the concept of electrode potential and cell. Look at the concept. What is an electrochemical cell? Electrochemical cell they are the modified version we are using nowadays, like batteries, like the dry cells. The conventional all chemical electrochemical cell, they involve a pair of electrode. One electrode will behave like a cathode, and one electrode will behave like a anode. Now, when you design an electrochemical cell, you actually make two half cell. What is electrode potential? When we first discussed this chapter, it's a concept when a metal is in contact with its own solution. When a metal is in contact with its own solution, then you get a half cell. Now, each half cell consists of an electrode and an electrolyte. Now, when you have a metal rod, for example, a metal rod is immersed in a solution of its ions, like an electrode, like any electrolyte, like copper in contact with copper sulfate solution, or zinc in contact with zinc sulfate solution. Anything can be there which is soluble in water, but a metal should be in contact with its own solution. Now remember the concept that when a metal is in contact with its own aqueous solution, the metal has a tendency to gain or lose electron. This will cause a charge on the metal rod, so the metal rod will become an electrode. Some metals are highly inert, like platinum. We use them when we want inert electrodes, and some metals like copper, like silver, they can be active electrode. If a gas is involved, like chlorine is the very common example, oxygen is the example, hydrogen is a very common example, the gas will bubble out. Now, half cell and reaction. A metal rod immersed in metal ion solution, an inert electrode immersed in a solution of metal ion, a gas is bubbled through the solution. Look at the example here. The first example is iron rod dipped in iron solution. Second example, solution containing equal concentration of Fe2 plus ion and Fe3 plus ion and platinum electrode. These two, all of these are very famous examples. And the third one, which is a special electrode, if you see on the right side, the special electrode where hydrogen is the input and the gas basically is coming out from the solution. These are the three important half cells. Look at these three examples, please. These are the three important examples. Look at the half equation. Fe2 plus 2 electron gives you iron, Fe3 plus E electron, Fe2 plus 2H plus 2 electron gives you H2. The half equations are important to show what's going on in the reaction. Now we move to our next concept. We make half cell to start the process. In every electrochemical cell, there must be two half cells joined together. The potential difference between the two electrode will cause an electric current. Achha, this concept is coming from physics. This is a concept coming from physics that if you have a positive terminal and you have a negative terminal and you connect a wire, what will happen that electrons begin to migrate. But this is not a complete circuit. Physics says you need a complete circuit for the movement of charge. So in physics, what we do, we make another wire connected downside. But in chemistry, we can't make such a two-wire or live earth system. We do that, we take a solution and our solution will contain charges. So if we put it in a solution and we have these charges which are in an aqueous solution, look at these ions also migrate. So ion migration is necessary. For example, -20 goes on this side. So logically, it has to be balanced by the reverse motion. So the net transfer of charge becomes zero. This is the basic idea in the design of an electrochemical cell. We develop a salt bridge which is connected between the two beakers, and we connect a voltmeter to show the potential difference. Look at this one. Cell representation: oxidation on the left side, reduction half cell on the left side. This is the conventional symbol M/Mn plus and Mn plus M. This is the conventional oxidation on the left side and reduction on the right side. Negative electrode is on the left side and positive electrode is on the right hand side. Look at this. In between, there is a salt bridge. Standard cell potential of an electrochemical cell. How we find it? This is the conventional point to remember the word standard. The word standard means we define some conditions. We define some conditions like temperature, like pressure, like concentration. Under these conditions, we find out the potential difference, and that is called standard electrode potential or standard cell potential if we find the overall. Then what's the formula? E phi of the cell is equal to E phi of the right hand half cell minus E phi of the left hand half cell. Or other way, reduction half cell minus oxidation half cell. We can also write the same formula as more positive half cell minus less positive half cell. Please look at this whole screen, and if you have any query or you want to add any point, you can go ahead, please.
So isn't there supposed to be like a platinum that you put in? Like if let's say if it's a platinum electrode, you put that on the left, right?
This is good, na? Look, actually what happens, whatever you want, look, it's a game of comparison. Who is your neighbor? So it's a rule, fluorine comes with chlorine. So fluorine is more electronegative. But when bromine comes with chlorine, then chlorine is more electronegative. So it's a comparison. So that is why we do not say who will always be on the negative side and who will be always on the positive side. It's a game of comparison. It's a game of comparison. Electrode potential. Now we introduce as a formality the most common cell which was initially was successful was Daniel cell. And this half cell of a zinc electrode is on the left side, and the half cell on the right side consists of a copper rod. And zinc loses electron more readily than copper, while in the half cell on the left side, which is the from the electrode rod, is oxidized to form Zn2 plus. Now, how we show this in the half cell on the right or on the left? We show it by equation. Look at this. This is the most famous, the conventional half cell. Left side we have a zinc electrode and right side we have a copper electrode. See the motion of the electron. Zinc rod is losing electron while copper rod is gaining electron. Zinc arrow Zn2 plus will 2 electron, copper 2 plus 2 electron and copper. So as we were discussing in the once I think in the previous slide, that how we take platinum or anyone, we always prefer here active electrodes. Platinum is used when you are doing the conventional electrolysis, like the electrolysis of sodium chloride or something. Here you want to see an inert electrode when you are dealing with a gas, like if you want to have a hydrogen half cell, then platinum is a good choice. If you want to make a regular half cell combination, then zinc and copper was the first successful combination. Now, obviously,
But in this one, it's like it's a metal electrode with a metal ion. It's
hmm,
a metal ion solution. So
yes.
and then and what's the other one? It's like you
Again,
have
on the right
no,
side, a metal.
it's non-metal non-metal something.
Huh,
I,
the second possible combination is non-metal like involving a gas like chlorine or gas
is it
like
like the same thing where like the electrode has that the thing over it, and then there's gas pumped in from the side at 100
huh,
kilopascals, right?
Just perfectly right. But that is, you remember, it was used to make a standard hydrogen cell. The most common of gaseous or non-metal electrode was hydrogen half cell. You pump in hydrogen and you make a platinum electrode that is used to find the electrode potential of any new cell. But when we make a commercial cell, we need those metals. Nowadays, people talk about lithium batteries and cesium, etc. So we need active metals. We use non-metals, for example, hydrogen's half cell, chlorine half cell, which can be used mainly for comparison. Now look at this equation. Overall redox equation, zinc plus copper ion, Zn2 plus copper. And this is basically the formula is also there. These values are given in our data booklet, or they will be given to us. So we subtract by the formula discussed. Now, look at the example. It's a redox system. And we have the famous equation MnO4, which is the one of the most powerful oxidizing agent in our course. Electrode potential is used to manage the combination of equation. The first equation is MnO4 minus, and it is turning into Mn2 plus, Fe2 plus. These two equations are so famous that now people, I'm sure you also remember the balancing and then multiplying and everything. Sometimes Fe2 plus converts to Fe3 plus, sometimes it's converting to Fe, which examiner will tell us that what relation is making it. And when you make the equation, look, one electrode is Fe, the other electrode is the platinum electrode with manganate solution. We connect them and now we have a cell. We need a salt bridge to complete the circuit. Do you remember what was the main function of the salt bridge?
It acts as a pathway for the ions.
Good. It is used to complete the circuit, and it is used to make a circuit in which electron transfer occurs. Now, what are the conventional when you write down the overall electrode? This type of questions come. So when the conventional representation of this cell, this is very important. They want people to write in a way that oxidation comes on left and right, then right. Look at this equation, double line and then single line in between. And when you write it, it always has to be like this. He says, write down the overall cell reaction. So you have to multiply the first equation by 2, second equation by 5, and then you subtract. When you subtract, electrons get cancelled and you get an equation like this. When you multiply, electrode potential values do not change and you get the electrode potential as 1.81 volt. Now we move to standard hydrogen electrode. We were just discussing about it. Look at this. hydrogen is pumped in 1 atmosphere. We have a dilute acid, and the conditions are the standard conditions. Now, what is the significance of hydrogen electrode? It is used to calibrate other half cell because we assume that the value of electrode potential for hydrogen half cell is always zero. Look at the equation and look at the way we write for this. And what was the main idea? That this electrode potential value is zero. So when you connect any cell with it, it will give the voltage, just like in our physics we have two electrical wires. One is the live wire and one is the neutral wire. Neutral wire is always at zero potential, similar to that. So standard potential of this value is taken as a reference. Now look at this idea. Hydrogen. Why hydrogen is taken? Because hydrogen is the lightest gas available. It creates minimum potential. And then look at this one. One side is 1 mole of HCl. We are pumping in hydrogen. And right side is copper. It means actually this apparatus will give us the half cell voltage of copper. This is the way you have to see this. And hydrogen half cell is used as a way to compare the potential of the other cell. It's like a comparing scale.
Okay.
So this is the idea. Now, look at this idea that how we write it. Platinum hydrogen half cell comes on the left side. Copper half cell comes on the right side. This is very important. Who will come on the left? Who will come on the right? Now look at another example. Nickel is gaining 2 electrons. Conventionally, all equations are written as redox. So now when we draw the equation on the same way, we draw the half cell with a salt bridge. Nickel electrode, we see that nickel is minus 0.26 and iron is plus 0.77. So it means iron equation is more likely to occur. So it means iron would be going to gain electron and nickel is going to lose electron. Why? Because nickel has less positive electrode potential. So we develop this equation by this way. Similar that we make equations. Now we have these on our data booklet. These are the values given. And when we mark the values, we always remember that the values with high positive electrode potential are more likely to do what the equation shows. The less positive potential means the equation has to be reversed, or they have less likely to occur, these equations. So look at this idea: strong reducing agent, and on the other side we have weak reducing agent. Then these type of equations we have already discussed, that reducing agent, oxidizing agent. Achha, this is one of their favorite questions. For example, chromium ion, Fe ions. We always remember that more positive will be more likely to occur. There are two famous methods. One is called reversal of the less likely to occur and add the equation. Secondly, do not reverse the equation, multiply, balance, and minus the equations. Overall, it's the same thing. And it depends upon whatever we remember, and we can do the same. Look, these are the equations involving the overall potential. Now, the positive values, as mentioned, and negative values are different because they show the feasibility. E5 cell is directly proportional to total entropy change, a very important concept. E5 cell is directly proportional to the total entropy change in a reaction. When entropy comes in here with electrode potential, it becomes a difficult concept. Now, this is the equation, and we can say R, L, N, K, where K can be any constant, Kc, it can be Kp, whatever you root. And then we have the overall equation, ln k is equal to delta S upon R is equal to NFE upon R. Now, what are the conditions? Sometimes Faraday constant is found in the older papers. Now, in the new papers, they are not paying attention to that. Their focus is only on capital R. Feasibility and extent of reaction. What is this idea? Can we use aqueous iodine to oxidize bromide ions to aqueous bromine? Look at the equation. I2 plus 2Br minus 2I minus plus Br2. Look at this equation. I2 aqueous plus 0.54 bromine, and look at this 1.07. Now we do the calculation. We write the first equation as iodine is gaining electron and bromine is losing electron. So it means we have taken the bromine equation reversed. Now when we combine, when we add the two half equation, our final answer is coming negative. When we are getting a negative value, it means that trip, in fact, it will occur in the reverse direction. So reaction is not feasible. It's very important to remember that plus minus is a limited feasibility. Plus minus is a limited feasibility. It doesn't mean absolute feasibility. In chemistry, we always say that sometimes you find a feasible reaction in terms of electrode potential. But other factors like chemical kinetics, entropy, or activation energy are also involved. Now you have this equation. Now feasibility, look at this example, predict whether or not H2O2 will disproportionate in aqueous solution. Do you remember what was disproportion in context of oxidation number? Where one species is oxidized and reduced simultaneously according to the following half equation. Look at the first half equation. H2O2 plus 2H plus takes one electron and it is 1.77. And then oxidation equation, if we reverse it, H2O2 gives you H plus plus O2 plus electron. Now, if we combine the two equations, we got an electrode potential positive 1.09. Answer is positive. So it means this reaction is going to occur. So we have, this is a very memorable thing to remember, that the value of K, E5, you're not supposed to memorize these values. Main thing to remember that it is a relative feasibility. Now, this is our concept we were discussing, that if a reaction has a high activation energy, even though the E5 will give it a go ahead, it will not occur because of high activation energy. Look at this example. Iron 3 converts to iron 2. It's a positive 0.77 electrode potential. Look at the second oxidation step. Now, when you combine, electrode potential is positive 0.46. But even though electrode potential is positive, the reaction won't occur because it has a high activation energy. From IGCSE, we know that if kinetically reaction is not moving, we can heat up the reaction. If it's a gaseous reaction, we can increase the pressure. So this is an example of some reactions where the rule goes, the rule is deviated. These batteries and these things are additional application. Whenever these questions come, this will be examiner responsibility to explain the features, the rules, like the hydrogen oxygen fuel cell, and they were in our IGCSE also. This is all electrode potential story, that one anode, one cathode, they make a combination of cell. Now we can make alkaline hydrogen fuel cell. Fuel cells actually got famous because their byproduct is only water. That's why they are safer. And compared to normal cells, they can be run continuously. Now this is an example of fuel cell. Now comes the title, redox titration. What is redox titration? It's a titration between an oxidizing agent and a reducing agent. We have potassium manganate 7 titration. Look at this oxidizing agent, potassium manganate 7 solution, reducing agent iron 2 ion, ethane, dioate ions, and indicator. Now, who is the indicator? The manganate ion itself is an indicator because it shows a color change when reaction reaches a endpoint colorless to pale pink when it is used in a typical solution of iron. This is important. Remember that you can use acidic solution also. So we can take a solution, we can take a 25 cm cube of dilute sulfuric acid is added. All the things you do for a conventional titration, but potassium manganate solution is added with in the flask. Acid comes from the burette and we observe a color change. Potassium manganate 7, then you can use this titration to determine the amount of iron in iron tablet. This is a syllabus example, but other things are also possible, like how much iron is there in a certain compound. Look at the reaction. MnO4 minus is the most powerful oxidizing agent. Normally we refer it turns into Mn2 plus. Look at the Fe2 plus converts into Fe3 plus. When you combine, you get the equation. And normally the color comes in because of the MnO2. So purple becomes colorless. And this reaction is like this. Now, variable oxidation state. What was the concept of variable oxidation state? Some elements like iron, chromium, especially transition, they show multiple oxidation state. How they can show multiple oxidation state? Like if I take iron, so iron can show me Fe2 plus, iron can show me plus 3. So, do you remember the role of variable oxidation state due to d orbital? Do you remember this rule? This contribution of d orbital.
Um,
D orbitals have vacancies. D orbitals are
yeah.
incomplete. Please go ahead.
No, it's fine. Yeah.
Okay. So the titration values, we can, whenever you are dealing with multiple oxidation state, the main idea to remember that actually this is again coming from the data booklet. You will see that some equations involve variable oxidation states. So the calculation is conventional. We're not doing much calculation work today because we are focusing on theory recall. Another important redox titration which got very fame is the iodine thiosulfate titration. I remember the last year the famous titration which is called the iodine clock reaction. Now look, iodine, iron 3, what are the oxidizing agent? Iron 3 ions, copper 2 ions, manganate 7 ions. Who is the reducing agent? Iodine liberated from potassium iodide solution. Who is the indicator? This is a very famous titration. Many people have done it in their school laboratory. Starch solution. Starch solution is used as an indicator. Starch solution is used as an indicator and it has a typical color change. It has a typical color change, blue, black to colorless. And now what's the procedure? Again, this is a typical titration. We take 25 cm cube solution of oxidizing agent in through a pipette in a conical flask. Then we take sulfuric acid. In that system, we add add H2SO4 to make it acidified. Burette is filled with standard solution of sodium thiosulfate, the S2O3 and S4O6 solution. Sodium thiosulfate is added steadily and then we allow the iodine and then reaction. When reaction completes, the color changes. And what is the main idea? Again, that sodium thiosulfate is then added dropwise until the solution goes from blue black to colorless. This is the idea. Achha, this is the titration which is being discussed in earlier classes also. Iodine takes 2 electrons and become H2I minus. This is reduction. Then who is doing oxidation? This S2O3 is the thiosulfate. It turned into S4O6. And then this is the overall equation, and solution changes. Now, what are the application? We use it to find the percentage of chlorine in bleach. These are the reaction. This is just like a sample, and different applications are there for this type of reaction. Again, we are bypassing the numericals today because this is not our main concern. Presently, we are focusing on main idea. We were focusing on redox. Now, this was the title redox chemistry. Now we move to our second title. I have shared a list of chapters, which obviously you have to revise also, and the whole syllabus have to be reloaded. Then some full yearly past papers, as usual, always memorizing the tables, important charts. Paper 5 obviously would be a very loaded paper. This topic is about transition metal, one of the most challenging chapter in the whole A level chemistry, AS or A2. Very challenging chapter. Multiple color changes, multiple concepts, multiple line of equations. So this is a really very challenging chapter. We are starting transition metal, then principle of transition metal chemistry. When we start with this, our first concept is the electronic configuration. When we see the electronic configuration, scandium, titanium, vanadium, and we go till zinc, we will observe the pairing. In scandium, the 3D orbital contain only one electron in the 3D, and 4s is full. So we had a concept that 4s is filled before 3D. 4s is filled before 3D. Then you see 4s is filled throughout, but in look at this in chromium. In chromium, you will see this in chromium. Look at this in chromium. Look at this idea. Z is equal to 24. One electron is given to 3D so that it becomes stable. And then when you reach the second last, which is copper, you will find a similar loss of electron here. And the 4s orbital, when it is full, it is stable. When it is half, it's also stable. Look at the 3D orbitals here. 3D orbitals are gradually filled. So it means in successive successive transition elements, we will find variable oxidation state. And I hope you remember the game of color. So scandium is colorless, so scandium is not a transition. Zinc ions are also colorless, it's also not a transition. But other colors are real big thing to memorize. We can say V3 plus is blue green, chromium 3 plus is violet green. I will share this sheet inshallah. And I think you have a sheet also which might be more organized, but you have to remember the color. Color is very important. You have to memorize all the colors. Now D block. What's the importance of D block? D block actually has a capacity of 10 electrons. It is divided in two groups. The total 5 sublevel. The 5 sublevels can be divided in two groups. Now, what is a transition element? In this D block reference, transition element is an element that forms one or more stable ions which have incompletely filled D subshell. This is the official definition. And whenever the definition comes in for transition, you have to mention it in terms of d orbital. In period 4, the orbitals lies there. All the elements from titanium to copper, and we deliberately exclude zinc and scandium because they do not show multiple oxidation state, and scandium atom forms only scandium 3 ion which has no d subshell. Look at this. And zinc also has the same problem. So we exclude them, but other compounds, they follow this. Now, they do not make colored compounds. Now, variable oxidation state, many of them, especially manganese, shows a whole line of oxidation state. +1, +2, +3 are very common. This is again a character of d orbital. From titanium to chromium, +3 is the most common one. These are the oxidation state. How they show multiple oxidation state? Because they have space in the 3D orbital. And due to the space, they can show multiple oxidation state. So you can see titanium, vanadium, chromium, etc.
Okay. And we have to learn all the equations to change the oxidation state for them as well, right? For vanadium and chromium.
I slightly missed the voice, so can you repeat, please?
You
Can you?
have to remember the equations, right? To
Normally,
convert.
uh,
Yeah.
but main equations are always given in the data booklet. The most troubling thing, is to memorize the color, which I always emphasize to my student, that memorize all the color transition. In every question, he will involve a color. Colors is the main thing. Formation of complex ion. Complex ions are those ions in which there is a standard ion surrounded by electron pair donors. What are ligands? They are called ligands. Ligands are molecules or anions with the capability of making coordinate covalent bond. Complex ion, an ion in which a certain number of ligands are bonded to a central transition metal ion by coordinate dative bond. And I hope you remember that there is a number, fixed number for every transition. Some can bind with 4, some can bind with 6, etc. A complex ion may be represented by this normal approach, and L is the ligand. So in complex ion, the transition metal sits in the middle. Like look at the right hand side, and here the ligands are surrounding it. Normally there are 4 ligands in our course surrounding, or 6 ligands in the surrounding. Now, when you have a classification of ligands, monodentate, which form one single bond, one atom, lone pair donation, and halide ions, cyanide ions, these are the ligands with monodentate ability. This is the example, aluminum example, and then you can make further examples related to neutral molecules. Water is a neutral ligand. Ammonia is a neutral ligand. Look at this. Cobalt is the center, and ammonia molecules are surrounding it. Now, bidentate. What are bidentate? Which can make 2 bonds per ligand. So 2 bonds can be made by each ligand. This is the example of bidentate. Di 1,2 diamino ethane, which is an example. And here, this is another example. This is where this chapter becomes very complex, because he gives the isomerism in this topic. And isomerism becomes a real challenge. Classification of ligands, then multidentate. Multidentate are those which can bind with multiple one, and the most famous example in our course is the EDTA. Has 6 sites containing a lone pair, and so it can form 6 coordinate bonds. Look at this multidentate. Look at the formula. I have taken some of these examples, the surrounding ions and the coordination number, formula of ligand, monodentate, bidentate, monodentate. Look at that. Now we talk about the shapes. When the ligands are surrounding the central ion, they occupy a certain type of shape. The shape can be linear, the shape can be tetrahedral, the shape can be octahedral. An alkaline solution is now, we can have the tolerance reagent, which is used to distinguish between aldehyde and ketones. Now, this is the linear ligand. It's a very famous reagent, tolerance reagent, which is actually a solution of silver and ammonia, and it's a linear molecule. Metal ions with a coordination number of 6 all atoms surrounding the octahedral shape. Now comes the difficult part, that these ligand structures display isomerism. For example, cis-trans isomerism. Look at this. Cis-trans, trans and cis. Compare it, and you can see that the A and A are opposite and the four B's are in the plane. And in the cis one, the two A's are in neighbor. Look at this one. And then it is different from cis and trans because they cannot be converted into each other just by rotating. Optical isomerism. This is again a very difficult thing. So people memorize this general shape. This general shape people memorize, and this is again the same rule is the same, that optical isomers are those which are mirror images. And we continue with the shape coordination number 4. Then the shape becomes tetrahedral. This is example of tetrahedral. This is example of tetrahedral. And then look at this tetrahedral example. All the examples are well famous and they always appear. So we can memorize them. And square planar, which can also display cis-trans isomerism. This is platinum, ammonia, and chlorine structure. And when you see this one, square planar means this is the shape. And it also shows cis-trans isomerism. Look at this cisplatin and transplatin, one of a very famous compound which is used in cancer treatment also. It is one of the most common repeating complex in our course. Then colors. This is again a topic which involve d orbital. We normally say that d orbital is used to explain everything about transition. They tend to form colored compounds and ions in solution. Most of the transition elements form compounds which dissolve in water to form colored solutions of complex ions. So this is called the DD transition. The d orbital actually consists of 5 sublevel and has 5 d orbital, and they actually comes in, these are the 5 d orbitals, but they do not have, all of them do not have the same energy. So when we actually have 6 ligands approach the ion to form an octahedral complex, look at this idea. The d orbital splits in a in a group of 2 orbital and in a group of 3 orbital. Achha, the group of 2 and 3, they can change position. Maybe the group of 2 is above and group of 3 is below. So this creates an energy gap. Colors of aqueous ion. So how color is produced? The energy gap is capable of absorbing certain wavelength of light. Now this is the idea. Certain wavelength of light due to which a specific color appears in the transition metal solution, ion solution. Now the energy gap in the split of d orbital ion corresponds to the energy of orange light. So the orange light will be absorbed and the solution is like this. So when so this is the processing of energy, and look at this blue color. This is copper, and copper ion solution is the most discussed one. Now aqueous solution, we have number of ion, and normally we have this card that different colors are shown. by different transition element, the rule is the same. In a transition element, the d orbital split into two groups. One group contain three sublevel, one group contain two sublevel. There is an energy gap between them, and according to quantum physics, this gap absorbs the wavelength of light in a particular wavelength. Now, look at the concept of change in oxidation number on color. When the oxidation number changes, the color of the color of the transition element changes. This is again a very helpful thing to remember. Iron complexes, when it is +2 is green, when it is +3 it is pale violet. Chromium complex, it is blue and red violet. Color is something which should be memorized because there is no other technical way to develop it there. And now we are talking about changing the ligand, the famous ligand substitution reaction. So a stronger ligand can replace a weaker one. And for example, when excess ammonia solution is added to aqueous copper sulfate solution, the relatively weaker water molecules are replaced by stronger ammonia ligand. This causes the absorption to move from orange towards yellow, and the color of the complex changes from blue to blue violet. Look at this color change, ligand substitution. Ammonia is replacing water molecule, and this is ligand substitution. Again, syllabus want people to memorize some of the colors here. Coordination number. What is coordination number? How many ligands are surrounding? For example, we have an octahedral. So if our coordination number change, the shape will change. Now, this is the copper with 6 water molecules. After reaction, copper is sitting with 4. Copper is sitting with copper is sitting with 4 chlorine. This is the color blue to yellow. And this is the color. Now we take an example of hemoglobin. Hemoglobin is a complex of iron, which is the breathing machine, and it is a molecule in our body which present in blood, which transport oxygen. This is the structure. Central transition ion is iron surrounded by nitrogen based links, and this is not to draw but to remember that it is a complex. This is called the heme group. This molecule has the ability to absorb oxygen. Now, we have the reactions of transition metal elements. Oxidation state of vanadium. Now look at this, oxidation state of vanadium. This is a topic which is coming from, number one, coming from electrode potential. And most of this topic is actually supported by support data booklet, but colors are to be memorized. This is an example of redox reaction. This is a redox reaction. Then look at this reaction. Oxidation number are changing. Look at them. All of them are color changes. Oxidation number changes. So color changes. Oxidation of chromium 3 ions by H2O2 in alkaline solution. And now look at this idea that chromium OH6 plus H2O2 gives you the idea of again, electrode potential is there to tell the reaction is going to occur or not. And these equations involve color change. Normally, we can say just like 4 to 5 posters are there, which have to be memorized. Reaction of transition now, deprotonation. What is deprotonation? Reaction with aqueous sodium hydroxide and aqueous ammonia. Look at this. Now here, the OH minus ions are given to the molecule, and OH minus ions are able to absorb H plus ion. This is called deprotonation. Then again, a color change is involved. And you can see all the way the color is changing. And now look at this ligand exchange. Ligand exchange reactions are the most common to come, in which a more powerful ligand replaces the less reactive ligand. So reaction with excess ammonia. reaction with excess ammonia. So we are having this copper H2 whole 4 OH whole twice with ammonia. So ammonia has replaced some of the OH minus ions. Then ammonia is replacing this also. These reactions are more or less a memory test. So you have to memorize them. Now reaction with concentrated HCl. Concentrated HCl, actually they support the transfer of ligands like water themselves. They have chlorine also, and they can provide chlorine. Here chlorine is substituting the water molecules. These are called ligand substitution, ligand exchange reaction. So ligand substitution or ligand exchange reaction involve the one stronger ligand replaced by is replacing the less reactive one. Catalysis. What is catalysis? Catalysis means that you have to speed up the reaction. Why we always talk about transition elements being a catalyst? Because they have d orbitals. They can offer both the types of catalysis, I mean homogeneous and heterogeneous. There are two types of catalysis to transition. Metals and their compounds can act as both homogeneous, heterogeneous. What is heterogeneous? Where in heterogeneous catalysis, we have the difference in state. So maybe the reactants are solid and the catalyst in gas, or maybe reverse. And homogeneous means catalyst and the reactants are in the same state. So now the game again goes for d orbital. Step 1, gaseous reactants plus active site, and the word is adsorb. Adsorption is the technique to remember. And then adsorbed reactants, they combine together, and then after the reaction is completed, they are released. So this is called the heterogeneous catalysis. Look at this. This is the mechanism of heterogeneous catalysis. Heterogeneous catalysis. Now, in heterogeneous catalysis, work because of the variable oxidation state. Actually, transition elements have incomplete d orbital. So, for example, vanadium 5 oxide is used in sulfur trioxide formation. Remember, the main idea is adsorption, where the ion can be combined. They make temporary bonds with the reacting species. Then homogeneous, this is again very famous. Some of the examples, especially iron 2 ions. Normally, iron 2 and the S2O8 cannot react because they are S2O8 and I minus cannot react because they are like charges. So we introduce iron ions which first react with S2O8, which forms Fe3 plus, and then Fe3 plus come back to its original state, but then I minus is there to change its oxidation number. What is autocatalysis? Autocatalysis is a concept where what happened that one of the product is able to catalyze the whole reaction. The famous example is this Mn2 plus, Mn2 plus, Mn2 plus. These are the ions which can catalyze the reaction. So this is the idea, and look at them, Mn2 plus ions. So they catalyze the reaction. And we have mentioned that this is a graph which shows that autocatalysis automatically slow down, because obviously when all the reactants convert to product, reaction stops. So we have done the we have completed, made a quick revision of transition, and repeating again, I will share some of the posters also. But the main idea to remember is to memorize the tables, the graph,